We are recording. All right, so, well, actually, yeah, this is going to be the last lecture that I'll give. So I'll cover 13.1 today, boundary value problems, and then Amber will do 13.2 on Tuesday. And then the thing about Thursday was that was meant to be a class for review for a written final that we're not doing anymore. So I was like, what's the point? So I'll be around. I may be in a heavily sleep-deprived state from flying during the previous night, but I'll be here in case someone has questions about the coding part of a final, or about if they haven't taken oral yet and are preparing for it. So we just won't have this. Okay. As you may have seen, if you get Canvas notifications, I put up one, I swear to God, last quiz on chapter 13. What? What?
Why did you add another quiz?
Because I am covering that stuff.
Oh.
What?
Is this
Is two quizzes on you?
Well, the one quiz that covers two sections.
Did I already do that one?
Yeah, that's on the 30th though, right?
No, there's one due Monday, and then he just added another one.
Let's do the third.
Yeah.
Okay, so that's one that I have.
As if due dates matter, but yeah.
Well, on
So,
Canvas it does, it locks it out, I think.
No.
Does
no,
it?
no, you
No.
have no. You can. I allow taking it late.
Oh.
Yeah. So, yeah, I've gotten plenty of submissions that it flags as late, but I don't care. So, well, the only thing that matters is that everything has to be in by like May 11th,
Okay.
because grades are turned in to the registrar the following Monday, and I'm not going to be taking in any new stuff over the weekend. Okay. All right. So I apologize if I happen to say that the previous quiz was the last one, because I hadn't even thought about the chapter 13 stuff at the time. But I swear to God, this is it, because we just aren't covering anything past that point. Okay. Yes.
Where does the oral exam final information end? With the 13?
Right.
Okay.
Yeah. So in other words, Tuesday's class. So
Great.
well,
Day
I guess
after my
that, well, not for you.
Oh, cool.
Because you will not have seen that section yet.
So Tuesday what?
Okay, Tuesday's class is the last class where new material will be covered.
Okay.
Yeah. So, well, it's also the last class. Period.
Yeah.
Since there isn't going to be class next Thursday. So what you see today, Thursday, that is it. As far as what could be included on the oral. I still only had a few people schedule that. So for the rest of you, try not to let that wait till the last minute. I mean, so on the days I'm actually here, which are Thursday and Friday of next week, and then Tuesday, Wednesday, Thursday of finals week. On those days, there's still plenty of openness. During finals week, I will not have my regular meetings with my research students that take up such a big part of my schedule. So there's a lot of leeway there, and there's a fair number of you that we have to get scheduled. I think only 3 or 4 of you are. Okay, actually, another thing about scheduling, I need, when it is scheduled, I do need an email from you, even if we've already talked about it, to set a time that's in conversation. Do not expect me to remember. I don't want to accidentally double book or anything. So please do that, because that way I'll have one folder where I just dump all that and say, oh, here's everybody's schedule.
How
And then,
long should we allow for it to take?
well, I prefer like an hour time slot, but
Okay.
probably would take more like 45 minutes.
Okay.
Yeah.
Are you gonna help us with that?
In what way? What do you mean by that?
Hints and stuff?
Like as in during it, or
Yeah.
okay.
Like if you ask a question.
Okay. what I will do is, like if there's something, if I put a question out there and you just don't know, I will give you some way of recovering, like trying to ask a different way to get there. So, so it's not something where like you get deer in headlights, and then all of a sudden you can like see your score slipping. There will be an opportunity to recover from that. And that's actually why I said, even though I expect it to be like a 45-minute experience, I'm allowing an hour to recover from freakouts. So it literally is for that reason. So, okay. Now, okay. Email's starting to roll in. That's good. Okay. Any other questions about that or the coding part? Oh, okay. From simpler mathematical times.
Right.
Yeah.
Using your unit circle. Find these out.
Okay. All right. So by tomorrow morning, I'll be in San Francisco, but don't worry, I will still be at my email like I am any other time.
So we can email you at like 2 in the morning and you'll still be up, because that's like what?
No, he went to bed at midnight last night.
That's an exception.
Well, it'll be a different time in
Well, it's 2 hours back.
Oh.
But literally, if you email me 2 in the morning, I will be up at midnight Pacific time, but I'd probably be up at 2 a.m. Pacific time as well. So,
But I know that I try not to blow up his phone afterwards. It's like, let me know when you're going to bed so that I stop sending those.
yes, you try, and occasionally you succeed. So.
I'm trying to be considerate of bedtimes. Also for Diana, anyways.
Okay. So, so I'll still be on call as usual. Okay. I know that so one thing I will try to accomplish while I'm gone, I know there's some homeworks piling up, especially homework 6. And yes, corrections, I still have a bunch of those to work through. Thankfully, those are quicker. But at the same time, there's still more assignments so I need to get those back to you, but there are also some things that you need to send my way. And please try not to wait until like May 10th. Because you do not want me deciding your final grades when I'm grumpy. Okay. All right. Okay. Let's see. All right. Okay, so I have 1, 2, 3. Okay. I have 4 emails from people who have scheduled, but I know there's been a couple more than that. Okay, so now let's get to the very last stuff. Okay. All right. So the unlucky chapter 13. 2-point boundary value problems. So we're still dealing with differential equations, like we have been, and some of that will still be useful, but now we're going to, but this will be a different sort of problem with different conditions attached to it. Also, we've been looking at differential equations of first derivatives. Now we're going to be looking at ones of second derivatives. Ooh, complexity. All right. And today we'll be focusing on one approach in particular to solving these, called the shooting method. And then on Tuesday, Amber will talk about a different approach, finite difference methods. So what is a 2-point BVP, so boundary value problem? So with initial value problems, IVPs, you had an ODE and you had an initial condition. So here it's a little different. We have, again, an ODE involving a second derivative y double prime is some given function that depends on your independent variable, which will now be x. So boundary value problems depend on space, whereas with initial value problems, your solution depends on t for time. So it depends on x, y itself, and also it can involve the first derivative, y prime. And that ODE is defined on some bounded interval, AB. Okay. So those are the A and B are the 2 points in the 2-point boundary value problem. And because it is second order, we need, good, more emails, we're getting there. So we need 2 boundary conditions. So BCs for boundary conditions. So we have y of A must be equal to alpha, and y of B is equal to beta. Okay. So the highest order derivative in your ODE determines how many conditions you need. So like for initial value problem, like y prime is f of ty, so first derivative, so we only needed 1 initial condition. Here we have y double prime, second derivative, so we need 2 conditions, boundary conditions. Okay. Now, okay. What I won't get into here because I'm more interested in how we actually solve these. So, like with initial value problems, we had an existence uniqueness theorem that stated conditions on your function f so that the initial value problem is guaranteed to have a unique solution. So here too we have conditions on the function f and its derivatives, like derivatives with respect to y and y prime, to again guarantee that there's a unique solution. So this is, we'll spend time today on how we solve one of these. So the first page of chapter 13, so page 45, those existence uniqueness conditions are stated. Okay. All right. Now, we've been spending a lot of time lately on initial value problems and how we solve those. And it would be a shame if all of that knowledge you have about initial value problems, or hopefully you have by this point after sitting through all that, is now thrown away and forgotten about when it comes to solving boundary value problems. Unfortunately, we don't have to. So the method I'm going to describe today, the shooting method, actually uses all of that material on initial value problems to solve this boundary value problem. So we're actually going to transform this BVP into an IVP. Okay. So, so the initial value problem that you'll solve is, well, the ODE is going to be exactly the same. Same interval as well. But now, even though we're thinking this is a problem in space, x going from A to B, we're going to think of x as like a time variable. So A would be like an initial time, and B is treated like a final time. So we're going to progress from left to right. So the initial conditions will be established at time, if you will, x equal A. So because it's a second order ODE, we need 2 initial conditions. Now, you've all taken well, okay. Yeah, I think I can say this correctly. All of you have taken a course on differential equations.
Very
Okay.
nicely worded.
Whether you remember that or not. Dang it.
Already?
Yeah. Okay. Well, I was, what?
At least I'm not in the bathroom.
Okay. Jeez.
I'm never gonna look at that one.
That's right. You don't have to try to remember to touch the screen now and then. Okay. Yeah. Well, the thing is, because Caitlin's not here, she hasn't taken differential equations, so since she's not here, I can say all of you have taken it. Right? Okay. Okay. All right. Whether it's Math 285 as for undergrad or 605 for grad. When you have a second order ODE, what are the initial conditions on? What kind of form do they have?
They have y and y prime.
Yeah. So y of a and y prime of a have to equal something. So the first initial condition will be the same as the first boundary condition, y of a equals alpha. And then y prime of a, we're going to set equal to t. Yes, what is t? And my answer is, I don't know. So the idea is, the second boundary condition is not part of this, because that's not what you would specify for an initial value problem. The idea is, on your interval from A to B, so if these are your original boundary conditions, like right here we have y equals alpha, and over here we have y equals beta, then the idea is, but t, whatever value you pick for t is, okay. So if I draw a tangent line here, the slope of that tangent line at x equals a is going to be t. So the idea is you are choosing the right slope so that hopefully your solution that starts at the correct value of y equals a will hit the target of y equals beta on the other side. That's why it's called the shooting method. You are choosing t, and the idea in mind of you're trying to aim for beta. And what we'll see, especially at least for nonlinear boundary value problems, we have to try to guess. You'll have to aim several times, and with each, and learning from your previous aim that's off to try to hit the target. Okay. All right. So the way we do this is we can now solve this initial value problem with these initial conditions after choosing a value for t. And then based on what happens, we can figure out from there. But it turns out that when we have a linear ODE versus a nonlinear, that changes everything in terms of complexity. So in fact, we could figure out the correct slope in one try when it's linear. So I'll talk about linear first, and then we'll get to nonlinear, that is much more interesting. That's what features in the, if you're doing the coding version of a final, there's a couple problems there. Okay, so the linear case. So in that situation, I can write the ODE in a particular form. So the idea is, when I say linear, it means that the function f depends in a linear manner on y and y prime, not necessarily x. So your ODE can be written in this form: y double prime is equal to p of x y prime plus q of x y plus r of x. So if you think of y and y prime as independent variables, then you can see that. So because right here, everything on the right side is your function f. That depends on y and y prime. So it's a linear function in y and y prime because there's no y squared or e to the y or anything like that. They're just y or y prime appearing by themselves. Okay. So what you can do is, here's basically a three-stage process. We're using the shooting method for a linear problem. So the first thing you do is you solve this initial value problem. Y double prime is equal to, so the same ODE, but with these initial conditions, y of 0 is equal to, not 0, a is equal to alpha. So the same initial condition on y, but you say y prime of a is equal to 0. So you can solve it by whatever means. Like if it's a particular simple ODE, like the kind you see in Math 285, you can solve it analytically. But the thing is, if I tell you solve this IVP, based on what you've seen in a previous chapter, chapter 12, what kind of ODEs did you solve then? Y prime equals f of ty, which is not of this form. So you're like, well, I don't know how to do that. Well, now I'll tell you. So you can write any higher order ODE as a first order system of ODEs. So I could define these variables. I'll let u1 equal to y, u2 equal to y prime. So this is a standard approach to converting higher order differential equations into first order ones. So what that means is, in this case, you have a system of two first order ODEs. So u1 prime is equal to u2 because that's y prime and that's y prime. By the way, this is a comma, not a 1. And then, what is u2 prime? u2 prime is y prime prime, which is y double prime. So that would be equal to p of x y prime, but that is u2, plus q of x times y, but that's u1, plus r of x. And your initial conditions, u1 of 0 is alpha, not a, not 0. Dang it. u2 of a, that is 0. So this is the initial value problem that you would actually solve using whatever numerical methods, like the ones that were covered previously. Like if you were to use, like for instance, you could use Euler's method on this, where now your yn, like y1, y2, y3, those are now vector valued quantities. And your time derivative, f of ty, is a vector valued function. So when I get to nonlinear problems, I'll show you an example of how you apply typical numerical methods like Euler's method or Runge-Kutta to something like that. One thing I did not cover, section 12.6. how you apply numerical methods to systems of ODEs. But when we really need that next section, that's something that Amber will flesh out for that particular case. I should tell her that. Okay. All right.
Is this the same thing that you do in 605 where you're just changing your variables and you have u as u prime and then you've got the
Yes,
v?
it's exactly the
Okay.
same thing.
I just want to make sure that that's what
Yes.
I'm seeing.
Okay, so those few grad students who took 605
Yeah.
are
I know how
familiar
to
with
do
it.
this.
Yeah. Okay. All right. So that's so you would express this IVP in this form before you actually try to solve it numerically. In fact, what I could do, I have the space, so why not? How you would solve this using Euler's method, forward Euler, just so you have the idea. So u1 n plus 1 is equal to u1 n plus h times u2 n. So that's how you would handle the first equation. And then the second equation would be u2 n plus 1 is equal to u2n. That handles the time derivative part. Plus h times all this. P of x. So really, instead of x, it'd be xn. u2n plus q of xn. u1n plus r of xn. So that's how the time stepping. That's how the time stepping would proceed for this. Like for n equals 0, 1, 2, and so on. Whereas if I were to change like anything that's multiplied by h, if I change all these n's to n plus 1, that's backward Euler. So if you look at the other time stepping methods we've seen, like Runge-Kutta methods, multi-step methods, it would proceed in a similar manner. Okay. All right. So we use this kind of approach to solve this initial value problem. Then you solve another initial value problem. That's going to be y double prime is p of x y prime plus q of x y, but no r of x. We do not include that term for the second problem. And the initial conditions, y of a equals 0, y prime of a equals 1. Now, when you solve these, sorry, I left this out. For a first one, we'll call that solution y1 of x for step 1. And then when we solve the second one, we'll call the solution of that y2 of x. Okay. All right, questions so far about what we're solving? So the third step, I'll explain why we're solving it. Because now you can combine these to get the solution to the original problem. Y of x is equal to y1 of x plus beta. Wait a minute. That's wrong. Okay. T y2 of x, where now I can tell you what t is. Because before I write down the formula for t, and actually I'm giving away a homework problem, but I didn't assign it, so there. Before I talk about the boundary condition at x equals beta, I want to talk about, not x equal beta, x equal b. Yes, I need the semester to be over just as much as you do. Okay. So, all right. So I'll talk about x equals b in a moment. In a moment, x equals a. Because what happens is if I plug in x equal a over here, and I plug it in over here, and I get alpha, which is what I want. And then I plug in x equal a over here, I get 0. So we don't step on each other's toes. Similarly, if I plug in x equal b, well, over here I want to get beta. Here I get 0. No. No, I don't get 0, sorry. But the point is, I get beta over here. I need to make this equal to beta also. Now, I don't know what t is, but y1 of x and y2 of x, I could just plug b into those and see what I get. And I can use all that information to solve for solve for t, which is my unknown. So what I can do is, if I plug in x equal b throughout, set this equal to beta, then I can solve for t. So I get t is equal to beta minus y1 of b, whatever that may be, divided by y2 of b. Okay, so in this case where we go ahead and solve these, okay. So we solve these problems, then we can use that information to figure out what the right slope is to use at x equal a to hit our target at x equal b. Okay, so sorry my preparation is lacking here. But, now, any questions about why this works? Well, one key point about why it works is it's because it's a linear ODE. Because when I take these two solutions, y1 and y2, if I take any linear combination of these solutions, they will be a solution of the original ODE at least. So that's one property of linear differential equations, or linear equations in general. You add two solutions together, and you get a solution. Now, R of x we only needed in this one. So with this one not having an R of x, that way it doesn't step on the other one's toes. It's kind of like when you have a solution of ax equals 0, and you have a solution of ax equals b. You add those two solutions together, you also have a solution of ax equal b. It's the same idea. If you remember anything at all from your differential equations class, when you're solving this equation, what you're getting is called a particular solution. Whereas when you're solving this equation is a homogeneous equation. You're getting a homogeneous solution. So then you're just finding a right way to combine them so that the boundary condition at x equals b is also satisfied. Now, one fine point here is that we're dividing by y2 of b. Well, you might ask, well, what if that's 0? It turns out that the conditions, well, I didn't state them, I referred you to the book about them. The conditions for this boundary value problem to have a unique solution, those conditions, if satisfied, guarantee that y2 of b will never be 0. So as long as you have that kind of well-posed problem, you don't even have to worry about that. Okay. So in this linear case, this is actually the less interesting case because we just solve these by whatever means. If we can solve them analytically, great. If not, we can use a numerical method like this to solve for both y1 and y2. Once that happens, we're done. We get the solution of the original BVP easily. It's when things are nonlinear that they get a little dicey. Because if I had similar nonlinear ODEs and I solve them both, I can't add those two solutions together and expect to have a solution of the original. So that goes out the window. So what do we do instead? we use material from chapter 10 for root finding. Okay. So for nonlinear DVPs, what we do is I'm going to define y of okay, check my notation here. Okay. So I can let y of xt, so I have a semicolon here to indicate t is like a parameter. The solution of the IVP I gave earlier. Y double prime is f of x, y, y prime. But f is now a nonlinear function of y and y prime. And y of a is alpha, y prime of a is equal to t. So I choose a t value. Whatever t value I pick, I solve this problem, and this is my solution. So I'm just using that notation y of x semicolon t to refer to that solution you get. Okay. Then what we have to do is to solve the original boundary value problem. We have to solve this nonlinear equation y of b semicolon t minus beta is equal to 0. So, because whatever solution we get to the initial value problem with whatever slope we chose at x equal a, if we plug b into that solution, we need to get beta. So you can think of this as a function. Well, I shouldn't use f. I'm already using f over there. Some function g of t that we want to be equal to 0. And I realize that using g invites confusion of fixed point iteration, but the thing in mind is we only have so many letters to use. Once I use a letter for a certain purpose, it's not bound to that purpose for all time.
Well, we can just say that this is not the first time that g has been used for a second function.
Right, yes, exactly. So we need to solve this equation by whatever means, whatever, like any of the methods that we've seen before, like bisection, fixed point, Newton's method, secant method, or other root finding methods that we haven't seen. The difference is, the thing is, you can use any of those methods. It's just that the particular function that you're trying to find a root of is a whole lot more complicated. It's not like the examples we saw in chapter 10, where I give you a function like x squared minus 2 or something. To evaluate this function at a single t value, you have to solve the whole initial value problem on the entire interval. You go through all that work, and then at the very end, whatever you get, you just plug in this one value, x value, b, and see, oh, here's what I get. Is it equal to beta? No? Then we have to keep going. All right, so what I'm going to do is show you how you would use Newton's method to solve this particular nonlinear equation. Now, Newton's method. What makes it a pain to apply Newton's method? What's bad about it? We need a derivative. And there are other drawbacks, but that's the drawback that is particularly vexing for this. Because what's our function? We're solving an initial value problem and then plugging in a certain x value. How do you take a derivative of that? Well, fortunately, we can. It might be a little difficult to wrap your head around, but we can do it. Okay. And the thing is, what are we taking a derivative with respect to? Well, it's our parameter t. That is our variable for our function. We need to take a derivative with respect to that. Okay. So if I let, okay. So we're going to solve that initial value problem for y, but, okay. So for Newton's method, what we need is the derivative of this function here, yb semicolon t, with respect to the parameter t, just because Newton's method requires a derivative. So for that purpose, I'm going to define a new variable, z. We can think of it as a function of x, so it's a derivative of y. So z of x is derivative of y of x semicolon t with respect to t. So the idea is y satisfies an initial value problem. We know what that initial value problem is. I've written it down over there. What initial value problem does z satisfy? Well, to find out, we go back to our initial value problem for y. And we differentiate, well, I'll also write down the boundary conditions, initial conditions. We have to differentiate those too. All right, so from this, what we're going to do is we're going to take this entire initial value problem and differentiate it with respect to t. So what we get is z double prime will be the derivative of this with respect to t. So we have to differentiate f. All right, so it's df dx, dx dt, plus partial of f with respect to y, dy dt, plus partial of f with respect to y prime. Now remember, y prime is a derivative with respect to x. I'll go ahead and write that down. So y prime here refers to dy dx, not t. And then we have derivative of y prime with respect to t. Okay. Well, x does not depend on t at all. Gone. So this whole term, gone. dy dt, well, that's just z. Now what about dy prime dt? Well, that could be worked out because what is y prime? I just wrote it down there. It's dy dx. So it's derivative with respect to t. So this is derivative with respect to t of a derivative with respect to x. But what I can do is I can reverse the order of differentiation. So I can say this is derivative with respect to x, derivative of y with respect to t. But dy dt is z. So this is dz dx. In other words, using this notation, z prime is what this is. Okay. All right. So that's what we have here. This is z prime. So now I can write down the other initial value problem we have to solve. So we solve z double prime is equal to df dy times z plus df dy prime times z prime. Okay. But we also have, we need initial conditions. The way we get the initial conditions, and it's on the same interval, x going from a to b. And what I do is I take the derivatives of these initial conditions with respect to t. Well, the first initial condition doesn't depend on t at all. So I get z of a is equal to 0. And here I differentiate this with respect to t. So what do you think z prime of a should equal? You're differentiating with respect to t. So we're differentiating that. Yes, because derivative of t with respect to t is 1. So now if we solve both initial value problems, the one for y that's written over there and the one for z, then we have the information we need to apply Newton's method. So, all right, so now what I'll do is I'll summarize all of this in one place and then show you how we can apply a numerical method to it, the root finding method, as well as solving the initial value problems themselves. So if you think things have gotten tedious and cumbersome already, just you wait. But, you know, it's my last lecture on this, so I go out with a bang.
Might as well have fun. A little bit of fun, right?
Yes, that's my joy, making everyone's eyes glaze over. Okay. But you all grow up to do the same thing as students, so. Okay. Doesn't matter whether it's about numerical analysis or college algebra.
You see it, and
Yeah. And to speak for mathematicians out there, like, just as I confuse you guys, they confuse me. So. Okay. So. Okay. So. So to solve this boundary value problem using Newton's method, we solve these IVP. So basically, I'm just summarizing. Y double prime is f of x, y, y prime. And also, z double prime is df dy z plus df dy prime z prime. Both on the interval a to b. And your initial conditions, y of a is alpha, y prime of a is t, whatever t you've chosen, z of a is 0, z prime of a is equal to 1. Okay. For each t, and then what we get from these solutions for both y and z, we can use in Newton's method. So the idea is t k plus 1, so this is notation I used for iterates before when solving nonlinear equations, is equal to tk. So in fact, I'll use that same notation tk up here. So you make an initial guess, and you go ahead and solve these initial value problems with that value of tk. And then the Newton step is what I'm going to write here. Now, Who remembers the main step in Newton's method? You have like xk plus 1 equals xk minus what?
Wasn't
F
it the
over
original?
prime.
Yeah, f over f prime, evaluated at xk. Well, what is your f in this case? It is your solution y at x equal b, semicolon, with this value of tk minus beta, because that's what you want to be equal to 0. So this plays a role of f of xk. Down below you have f prime of xk. Well, f prime in this case is z. So that would be z of b. Okay. So that's your Newton step. So what happens is you carry out this step, get your new value of t, solve these initial value problems again with the new value of t, and hopefully you hit beta, or at least you should be getting closer to it. You keep doing this until you achieve convergence. Okay. Now, like I mentioned before, in the linear case, you have two second-order ODEs to solve for these two IVPs. But you need to, in order to solve them using numerical methods, like Euler's method or whatever, you're going to convert to first-order systems. Now, a second-order ODE gives you two first-order ODEs. Well, we have two second-order equations, so we're going to have a total of 4 first-order equations. So we're going to have, so I'm going to let y superscript 1 equal y, y2 superscript 2 equal y prime. These are not powers. Again, these are not powers. These are not exponents. I'm not squaring anything. Okay? All right. We need superscripts from time to time for other purposes. And then similarly, z sub 1 equals z sub 2, or sub 2 is z prime. So those are my new variables. So now I can write down my 4 first-order ODEs. So I have y1 prime. Okay. Oh, I see what I did. I use different notation for derivatives, but okay. Okay. y1 prime. Those are not two ones. One's a 1, one's a prime, I swear to God. Is equal to y sub 2. Okay. In the book, I use like d over dx. That might have been better. Actually, I'll just do
I'm
that.
gonna do the detailed one with the little like cap in the bottom.
What?
Do the one that's like it says it's the line, the one I did. Open. Never mind.
I have no idea what you're talking about. Okay.
1,
Oh. Okay.
like you did in first.
Yeah. Okay. Okay. I was like, what are you doing? Okay. It's like you're making a perpendicular sign or something. Okay. So, all right. So this would be equal to f of x, y detailed 1, y2. Okay. And then we have dz detailed 1 to x, and not letting it go anytime soon. C2, and then z2 dx is equal to df dy times z1 plus df dy prime z2. So these are your 4 first order ODEs to solve. And next to them, I will write the initial conditions. So y1 of a is equal to alpha. y2 of A is equal to your current guess at tk, whatever that might be. Z1 of A is 0. Z2 of A is 1. So that's what we need to apply whatever numerical method like Euler's method or Runge-Kutta method to solve. Okay. Now, I'm going to lay out the whole algorithm so you can really see how whatever time-stepping method you use, like Euler's method, as well as Newton's method, work together. But before I do that, can anyone see, just from what I've written here, what's problematic here about using Newton's method based on having to solve these equations? Like, what kind of information here? Like, assuming you're given the original problem, like you're given f. What's the problem of using this approach? Yeah, these derivatives, df dy, df dy prime, those might be hard to come by. Certainly in software, you might be asking the user to provide them, and that's going to inconvenience the user. When you could use like a different root finding method, like if you're using secant method instead, then you don't need these two equations at all. You just only need these two. Yes, it converges more slowly, but not that much more slowly. So, so this may not be the best approach, but this is as bad as it gets. So it's a trade-off: rapid convergence versus all this complexity. Okay, and to really see that, I will lay out the algorithm, and then I think I'll be able to relieve you of your suffering.
He likes to suffer.
Every setting in life has their messages. Okay, so if we were to solve this using Euler's method, in combination with Newton's method, okay. So one parameter that we need, since we're solving this numerically, let n equal the number of interior x values, because we want to compute the solution at equally spaced x values between a and b. So here's our interval ab, and we have equally spaced x values, x1, x2, x3, and so forth, all the way up to x capital N. So we're going to compute the solution at those interior points. We already know what the solution is at a and b. It's the boundary conditions, alpha and beta. So the spacing will be h, just like for initial value problems, because we're going to solve this as an initial value problem. Okay. So now I can define h. So h is equal to b minus a over n plus 1. So that'll give a right spacing given n points inside the interval. Okay, so, and we need an initial guess, t0. Now, I'll talk, after I write this down, I'll talk about an initial guess, how we might choose that. So now we'll go into loop. So the outer loop will handle Newton's method. We'll have an inner loop for Euler's method. So this right here is Newton's. Okay. So my inner loop will start at like I equals 0. So I is for time stepping, K is for Newton's method. I'll set my initial values. So y0, 1 is alpha, y02 is, tk. My initial values from over there. z01 is 0, z02 is equal to 1. All right, so those are my initial conditions. So now, I'll just write this in the book. I actually don't need this here, because my loop will go from 0, 1, 2 up to n plus 1. Okay. Actually, I need to make a note of that. Okay. All right. So in here, I will use Euler's method. So I'll have y1 I plus 1 is equal to y1I plus h times its time derivative, which is this y2. Similarly, y2 I plus 1 is y2I plus h times its time derivative, which is f of xi, y1i, y2i. As far as xi goes, xi, formula for that is a plus I times h. So we've equally spaced x values. And then for the z's, z1 I plus 1 is just z1I plus hz2I. And then z2 I plus 1 is z2I plus h. And then we have this big mess over here, df dy at these same values that we used with f a little while ago, times z1I plus f y prime, that derivative, at the same values, y1I, y2I, times z2I. Okay, so just mimicking the ODEs that are written on the opposite board. Dang it. Sorry. Okay, and then the last step is, I wrote down earlier, the Newton step. So we end this loop, and then I have tk plus 1 equals tk minus. So I need the value of y at the very end. So that would be y1 n plus 1 minus beta, because that's the value at the right endpoint, divided by the ending value of z1 n plus 1. And then that ends the whole algorithm. So the outer loop ends as well. So we just keep, so at this point is where we check for convergence, and we'll just keep going until we have convergence of tk to a value. Now, so I'll emphasize right here, these two lines are not needed for other root finding methods, such as fixed point iteration or a secant method or bisection. So you can definitely save yourself some computational expense there at the cost of more iterations. And each iteration is expensive because you're solving a whole, because everything here, that's one iteration of Newton's method. It's an expensive iteration. So, and they're even more expensive if you're using Newton's because of having to do all this. Okay. Now, The only thing I've left out is how do you choose initial guess? So one extremely simple way to choose initial guess, well, t is a slope. So I could do, for instance, t0 is just the slope of a line passing through both points. So beta minus alpha over b minus a. That's one way to do it. So that's the linear function that passes through the two boundary points. Now that doesn't take into account f at all. So another way to proceed is if I let y of okay, basically if I just take one time step going from A all the way to B in one shot, I could solve this equation. Beta is equal to alpha plus HF of, okay, so in F, I plug in x equals A. Here we have alpha, and then here we have t, which is because t is equal to y prime. So for instance, if it's possible for you to solve that equation for t, that might serve as a good initial guess. But depending on f, that might be a difficult equation to solve in its own right, so you might not bother. But it's one way you could go. Okay. Or actually, what I meant to think of here was, all right. This is a problem. Okay. So for instance, another approach might be, here we assume the solution is a line. Well, what if you assume that the solution is a parabola? So you have something like this, so you have solution that passes through these points. And as far as the parabola, you use the fact that the parabola to impose a third condition, like maybe taking into account f. So if you can use, like I said, use f to determine a slope here, then maybe you can use that to also get an initial guess. So there are different ways of getting initial guess. They're very simple-minded or maybe a little more sophisticated. Okay. Well, I'm pretty much out of time anyway. So this is one way we can leverage our knowledge of how to solve initial value problems to solve a two-point boundary value problem, which can be used to, for instance, to model motion of a spring, for instance. I remember covering that in 285. So like a harmonic oscillator is an example of a practical two-point boundary value problem. So on Tuesday, Amber's going to look at the two-point boundary value problem in a whole different way, not using stuff from IVPs, although root-finding methods will still be relevant, to get a whole other approach, which actually I think is a better approach. But we like to use what we know in any way we can. Okay, so I will see you when I give you your oral final. For those of you who do that. Something to look forward to, I guess.